agent-based modeling.
Thank
Welcome.
you. Thank you very much. Hello, everybody. Hello, everybody online too. Thank you for this introduction. So today's talk is about agent-based modeling, in short ABM, and we're going to keep it a little lighter in the whole discussion. So this landscape is very broad, and therefore this talk is also intended to be kind of broad. And I will show you a few applications, not go into the details, into the depth of it, but we will discuss what actually agent-based modeling can be used for and what different aspects might be of interest for different research fields. So first of all, of course, I will give you a little bit of a basic idea of the research field, why we use agent-based modeling, and that is actually the system perspective. And then we discuss a little bit about how to design these agents. What is this main ingredient that agents need to be understood as a modeling component? And agent-based modeling is actually promoted by different platforms where you have software packages. We're gonna name a few, and then we're gonna play around with some educational models. So I'm going to show you a few things with the models live, apart from these slides, but we will also discuss some more scientific applications which are done here at this university as well. And I will end with a short conclusion about what agent-based models can be used for and what might be the limits of agent-based modeling too. So the system perspective is actually now embedded in something called complex systems. And collective behavior is some of these main ingredients that we focus on when we do agent-based modeling. And why is that? Because if you have individuals that also interact with each other, they form something which is more than the sum of themselves. And that is emergent phenomena from these microscale interactions on the macroscopic layer, for example, a societal dimension. And in short, if you explain now this collective behavior, you have very different tools. And for example, you see it here. I hope it's this, yeah, you see it here. Agent-based modeling is this part of complex science, but complex system sciences is split in very different parts. And we will also discuss a little bit here about networks. We will discuss a little bit about pattern formation and overall what system theory actually means in that sense. Agent-based models is one of these computational approaches that we can use now to model adaptive complex systems. And adaptivity is one of these main features that is very important to understand if you want to know more about complexity. Because if you have a system that you don't know how it's going to react, to some sort of external perturbation, you have to be in some sort of adaptive way to respond to this. And that means also that this one individual or this one part of the system that is actually perturbed by some external force, now through these interactions of these individuals, this perturbation can travel forth towards the system. So some sort of diffusion happening. And therefore, all of these individual units or agents are somehow connected and they form this emergent phenomena. Okay, so what we can now observe here is not only emergence but also something called self-organization. What might happen in this system now, if you look at the system, this is, for example, this population state, they can have some stationary states. You also know that from the Earth, where you have a white state, meaning that is the ice age, and the green state, what we are living right now, with a lot of plants on the Earth's surface. But what can also happen is that you found some sort of out of equilibrium behavior, some sort of non-stationary behavior, meaning the system also shows fluctuations, and it's not just this one fixed solution that you have, but these spatiotemporal patterns that form, they can develop over time due to these complex interactions residing beneath. And this is what we also call now self-organization. For example, you have stop and go waves in a traffic flow, and if like this passenger car before you is stopping, you stop too, the next one stops, the next one stops. That's just a simple way of describing traffic in a sense of self-organization. Also important things, of course, it has to be some sort of robust, so some sort of robustness has to be there, and tipping points are also very interesting. So if you have a system, it also shows some sort of resilience towards a specific type of behavior. And if you make the system successively less resilient, it approaches maybe a tipping point. And if this tipping point is reached, it might collapse. You can think about a Kreisel, some spinning top. And the larger these fluctuations are, the less robust it is towards this spinning around, and then at some point it will drop. And this is this tipping, so to say. And that can also happen now for more complex systems. And it cannot go back to the spinning by itself, right? Okay, so we have now discussed a little bit about this systemic behavior, and now what has that to do with these agents? They mainly consist of three ingredients, which are these agent-agent interactions, so among themselves, peer-to-peer interactions, but they can also interact with the environment. And the next thing happens that they show some kind of response towards this action and might change their behavior because of these interactions. So we have some sort of action, an effect, and then a feedback loop in the system. And that's basically it for what we want to model here. So this interaction, what we can model, there are three categories which I decided to distinguish because they have a very different visual component here too. If we just look at movement, we have some sort of topology, and these agents just move around on this topology like they want to, a little bit fuzzy, a little bit noise in the movement. And what you see here are some sheep and wolf we will discuss later on as well. They just move around on this plane. What can also happen if you have some ants that forage for sugar, and if they find sugar, they will emit some sort of pheromones which guides other ants towards the sugar, and therefore they can then collect the sugar to their nest in the center. That would just like also be some sort of a very simple application of what can be looked at. Another thing which is also connected to actually movement here in this plane, but it's a little bit different, is this grid movement. So you see here these locations are that each of them has neighbors, like these 4 nearest neighbors or 8 nearest neighbors, how it depends on how you will see it. And so they can hop, for example, this blue can hop to a white location because it is free if it chooses to do so. And another example would be not just this segregation, what we'll look at later, it's also here these agents were hopping as far as they could see to a more yellow space, which means that they found a space which is, again, higher distributed with sugar. It's very similar to this movement, but now here they just can locate again on this grid. So there are different ways of treating a problem with different solution options. And another option, which I will discuss later on the next slide as well, is this network application. It's very important here. The interaction is not really like we see it here on this topological graphical plane, but it is given by linkages. So you see the linkages here in white, and the neighbors that they can interact with, they are their link neighbors, so to speak. And the fusion now, if you have like this red dot and it wants to change its neighbors also to red, to its own colors, now travels only through this network. That can also happen, for example, with trade. This example is all taken from the Kansas libraries. I won't go into details, but just for an example, this is here a fish source, and then it's explained how with this model and a few data, a little bit of data was put into this as on a trade market, and then it was just put in a model, and this trade network is now done with this network linkage approach. So networks themselves are connected to a mathematical theory called graph theory. And as I already said, we just have these two components. We have these nodes and the linkages between the nodes. And the nodes are represented now by these agents who are now based on these rules of their behavior. And with these agents, they don't have linkages or not any link with, they cannot interact with them. Okay, so that's important to understand that we have a different sort of topology, so to speak. And this topology now, if you scale this, you can say, for example, each agent is randomly linked to another agent. And then you won't see really much of a topology structure for the whole population. You can also do it very orderly. So here in this lattice, all of the agents have 4 neighbors, and the neighbor of a neighbor is also now connected like just as a stepwise ladder, so to speak. It's just a grid that you can also do. So this is a large world, and you find this in a lot of applications. But more interestingly, especially now here, since we focus on societal behavior, is something that is found in societies, which is this small world and this scale field topology. The small world topology is that you have some shortcuts between actual nodes that would be without these shortcuts very far away from each other. And far away means very many different nodes are between one and the other. But here, this shortcut now helps these two agents to interact even though they are topologically speaking, they would be far away from each other. An example would be the actor network, because it has been shown that for actors all over the world, there's a very short stepwise linkage between, excuse me, how many steps you can have to, or how many people you have to know until you know a very high VIP, somebody who's very, very famous from Hollywood. And this short steps is actually 7, I think, 6 or 7 people that you have to know until you reach a VIP person from Hollywood. Another important network model is the scale-free topology. So here you have some hubs, they are highly connected, and you have a lot of individuals that just have 1 or 2 links, so they are very lowly connected. And these hubs are therefore some sort of centers of information. You can, for example, make a friendship network out of that. So a lot of people, or some people have very, very many friends, and some people have like a normal number of friends, and then there might be a lot of people that do not have a lot of friends. That's often done with these type of networks. So, and that was just for the introduction part of the scientific basis. Now just for what we're going to look at. There are software packages. I already said that we have a lot of options, but object-oriented programming is something that you should choose for your agent-based development, model development. Actually, it can be accomplished in any program language that you want to choose, but object-oriented programming is much more feasible because here these agents can be conceptualized as an object, as a unit, so to say. There are many very established platforms like Swarm and Repast. I also put here the links from all these examples. But what we are going to look later on is a little bit to play around with NetLogo and its library. I also put for your information here these software libraries where you find even more than just NetLogo and Swarm and so on. So there are very, very many. And also here is a Wikipedia link where they compare the pros and cons of these different platforms. So, but what we are going to do now in the beginning is to look at some free online models, some libraries where we can just play around, toy a little bit on what agent-based models can do or what can they be used for. But they will be a little easy on that side. So they also call toy models because they are just for visual learning, so to say. But of course, you can implement a little bit of these too. But let's start with this. And I will switch now, and I hope everything works. I will sit down for this. I will switch now to NetLogo. So where is it? Okay, so this is this platform of NetLogo where we find a free library. If we just download it, it's also for free. And this model library offers us quite a few models. You will see that. So where do I have to go? Evolution. Okay. So I will go here to this library, and you see that there are very many sample models from mathematics, philosophy as well, psychology, social sciences. What we are going to look at first is something in biology, evolution, and we're going to look at this. Where is it? Well, then it was here. Okay. All right, the wolf-sheep predation. So this is a population dynamical system. That means that we are going to look at the population dynamics over time about these wolves and sheep. This is connected to the so-called Lotka-Volterra equations. And this model is a simple application of these equations, or inspired by these equations. It's a better saying for this. So I just click here now on this setup, and we can now just initialize a specific number of sheep, a specific number of wolves. So I have 100 sheep and 50 wolves in the beginning. And if I now click on Go, I will start this timeline of these sheep. And what you also see is that these sheep are eating the grass, and the grass has a sort of regrowth time. For the system dynamics, now what would be called a stable state if all of these species survive over time? Even though you see here fluctuations in the proportion of each of the agents, you will see that they actually go up and down and are so-called stable because none of them go extinct. So, but why can that happen? Agent-based modeling is prone to a lot of control parameters in that case. It's better just to have a few, and here we have, of course, these initial numbers. You can also change that if you redo your setting, but also you can change how much each sheep gains from eating a patch of grass. And also what you can change is how much a wolf gains from finding a sheep. And we can also here have a sheep reproduction and a wolf reproduction as an additional control parameter. So for example, what would you think happens if I put the food reproduction very high? You have an idea what might happen? Just guess. So if they reproduce a lot, then you have quite a pressure on the sheep, right? Because here these wolves, they will get some sort of advantages in their numbers, and they will start to eat more and more sheep. So over time, if this reproduction is very high, the sheep will have a problem. However, this is not so much the case as you see right now, because these hungry wolves also tend to die out. What it would also need to increase is how much a wolf gains from the food. And what you see now, oh, I didn't do it, right? So let's try again. Oh, my wolves died out. That happened too. It's, of course, by chances. So this is one of these scenarios where we have an unstable situation. So the sheeps now are the only ones who are still interacting, and the wolves have died out. So there are several different scenarios we can find with the system dynamics. And the one is that the extinction of sheep is the first one, which of course is then followed by an extinction of the hungry wolves. But what you also saw in the beginning is that this population is stable. So even though there are fluctuations over time of the population sizes, none of these die out. But also what can happen is this extinction of wolves, and that puts a lot of pressure on the grass. So what happens that periodically these two pictures switch. So sometimes these sheep don't find enough food and therefore then they die out. And if they die out too much, the grass can regrow enough such that the sheep again have very much to eat and a population increase happens very fast. And then so we have still some dynamics here visible in the population dimension. Okay, so I hope this was already interesting for you, but now we will go to another toy model, mainly this segregation. I already told you before, now we have this grid movement. And this ABM was inspired by Thomas Schelling. He wrote a lot about social systems, and he was looking into the factors that are that are behind this phenomena of segregation in a society. So I have to go, I think, sample model, social science segregation. Okay. So, or just segregation. That's easier. Huh? Okay, we have different coloring here. Okay, never mind. All right, so again, I will now initialize the world. And here, these are two different colors, and now it is a green and a red, but we just have these two agents with their color. They think that green agents are more closely to them, or they want to be surrounded by green agents if they are green themselves, and red agents want to be surrounded by a specific number, not all of them, but by a specific number of red agents too. And you see, I hope you can see it, that some of these have a little X, a little cross on their patch. And that means that they are not satisfied or unhappy with the current situation of their position because, for example, you see this one here, this red guy just has one other red neighbor and the others are green. And it is just now a preference of wanting to be close to another agent that is an in-group preference, so to say. And this was actually very interesting because people thought before that segregation needs some kinds of an avoiding behavior, but actually with these experiments it was shown that this in-group preference is already enough to produce patterns like this. So what happened, I clicked on go, and now they decided they want to relocate themselves on this plane. So if I do that stepwise, you see that here on these black dots, they can go. And if I now do that, you will also see that the number of the unhappy agents goes down. And what you find here is some sort of pattern formation. Now it's not random or just randomly distributed on this plane, but you find some sort of pattern here of this clustering of this agent position. Okay, so that's also something we can play around with. And there's so many more models just to test out in these libraries. So if you're interested in learning about agent-based modeling, this is a nice way of getting to know just what it is about. But of course, in the end, you have to do a little bit programming. NetLogo has its own NetLogo programming language, but as I already said, there are many, many tools you can use. All right, so now we start with a little bit more of the modeling we can do for scientific purposes. And what I'm going to talk about is something I am interested in, namely the road from more verbally formulated models, as they tend to be present in psychology, for example, towards more mathematical or formally represented models, as they tend to be present in computational modeling and mathematics. So I'm, as already Florian said, I am interested a little bit in the climate debate, in climate change and social challenges around that. So it is very interesting to look at this climate debate and the entanglement of our reactions towards climate messaging. And the climate debate also revolves around a lot of threat, this perspective of chaos, of crisis, of catastrophes, and so on, is not very making us feel very well, right? It is giving us some sort of tension or anxiety. And that is actually explained with a nice model by Jonas et al. It's called the Integrative General Model of Threat and Defense Processes. So it's general, it doesn't work only for this climate debate, but it works pretty well here too. And what we have is now this perceived threat of a climate message. So you say to people it's going to be catastrophic, and that induces some sort of threat and will produce a reaction. For the climate debate, these reactions that we commonly observed are just this climate anxiety. So it's also called eco-anxiety. People don't feel very good thinking about climate change. They have some anxiety, arousal about this. And what we also find is that this skepticism about climate change is also a reaction that people tend to do when they are confronted with this information. They just say, no, I don't believe it. And others say, okay, I will opt for a more climate-friendly lifestyle because I do not want to contribute to its problem, but more to its solution. And all of this reaction now can be formulated with this integrative model from psychology. And it works like this, that first, that is divided in these two behavioral systems. The one is inhibitory, and the other one is a behavioral approach system. And if you have some sort of climate anxiety, some unsolved or anxious arousal that need to be dealt with, and also symptoms such as avoidance, they are more associated with this BIS reaction, so with this inhibition system. And if you seek an effective solution to the problem at hand, as in our example, this climate-friendly action, this indicates an approach-oriented reaction, which is now, if you want to use the climate debate as a tool for inducing more climate-friendly behavior, would be what we want to increase, right? Okay, so what happens now is we can take this verbally formulated model and use it for agent-based modeling and make a more formal model about it. How we do that, I can't go into the specifics, but we need a lot of data, of course. We need a lot of knowledge from psychology, how people really react, and all that influences several functions on responses now our agents can have. And these agents react, so to say, to this negative or threatening information by some sort of increased anxiety, and this is mediated by skepticism. So the more they believe in it, the more anxiety they can also generate through a threatening message. But also environmental identity is a very important moderator, but not for this anxiety, but to a transformation of the reaction through this approach motivation. So what we actually want to increase now, for example, climate-friendly behavior. These agents now can communicate about what they hear, they communicate about these messages, and so this agent-to-agent interaction also now can travel and diffuse here some sort of behavior through this social interaction network. And what we find, first of all, is by this diffusion of how they're interacting with each other, that these opinions that they have are over time polarized. So if we start with agents that don't have a very strong opinion on the whole topic, and in the long term we put a lot of threatening messages again and again and again into this model population, they will polarize. And they will have very strong believers of the topic and very strong skeptics on the topic. And the more threatening messages we put in there in a short time, the stronger these opinions also get. And what's also interesting is that if we have more climate skeptics in one population, the overall anxiety is, of course, a little bit lower because they don't believe it. However, the individuals that believe it are even more anxious because they realize they are not in the majority here and it's not really going to happen. So, and what we can also see is not just this opinion dynamics and this anxiety, what they have, we can also look a little bit about the intention changes. So, does the climate debate have an effect on my little agents here that they opt for a green behavior? And the answer to this is there are very narrow conditions that the majority of my agents tried to or responded to with approach motivation. First of all, they have to have very high environmental self-identities. I didn't discuss it earlier on, but it just means that you think of yourself as a green acting person beforehand. So just information just motivates you if you already have the right mindset. Also important is that this information density always has to be present. If it goes lower, if it's lowering out, if you don't present them with a lot of information in the long term, they also forget a little bit about this topic too, at least my little agents. And also they have to be open from the beginning. So meaning that if the whole population is very skeptic from the start, they will not, with this threatening information, be conveyed. They will not really start to believe in all this by threatening messages. So what this model does and what we think about is now hypothesis what that could mean for a real population. What does it mean if we just put threatening information in a society? Maybe we should diversify information and make it more solution-oriented. Will that help out the responses if it's not just a threat, but also what we can do about it? So there are a lot of hypotheses that we can test on with further studies and experiments from psychology, but just one additional complication, these agents in my population, through to these threatening messages on and on and on, were anxious all the time. And in psychology, there is a phenomenon where people, if they're anxious, tend to release the anxiousness, but maybe not with the problem at hand, but they will choose a Stellvertreterkrieg, so to say. So they will try to release the anxiety at something else. And it has been shown by other people than me, for example, Uhl et al., that people might, if they are anxious, might tend to ethnocentrism, for example. So there are very many problems that arise when we have an information stream that produces anxious populations. Okay. Just one more thing, what we also want to know here, is there an optimal solution about information? as far from these experiments, the problem is the more threatening information we put it in, the more climate skeptics we came out with. However, the more information we put in, the more climate-friendly agents behaved. So there was some sort of partial offset of this disadvantages that there are more climate skeptics. But overall, unfortunately, there was no optimal solution what to be doing with threatening messages in the long term. Okay, so this is the last model I'm going to talk about. And I hope you remember from before the segregation model. The segregation model is a classic from ABM, a classic in social sciences. And traditionally, as I already explained to you before, these agents need rules. So they behave on some sort of predetermined rules. I already explained that here, these agents, if they are orange, they want to live, for example, near at least 3 other orange agents, or the same goes for the blue one. So this is a hard rule. And if these agents do not meet these conditions, they are not satisfied, and then they have to move. So this decision-making behind all of this is actually relying on very many simplifications and assumptions to make it happen so smoothly. And here at this university, Georg Jäger is studying a new approach on agent-based modeling, which includes neural networks. And he tested his approach on this ABM of the Schelling model, or some variant here of the Schelling model, and he does not define any rule of the agent behavior. What he actually used is an utility function. So it just means if you are better off in the next round, you did something good for you. But what you have to do and how you have to do it, he didn't put in. So there are no hard rules. So this actual decision-making goes on with the sensory input of the past experience just of this utility. And now we need learning, because you just can have like one round and the other and don't have rules. You also need to know what you want to do in the long run. And these you can now here do by experience, which is induced by artificial neural network. Very, very easy to understand if you just look here at this. So neural networks typically have 2 phases. First of all, they are trained. And there you just have like this sensory input. You look at your surrounding. Do I like it? Do I not like it? And then here you make a random decision and you find out for yourself as an agent, do I like the result or not? This is the training phase. And now, after the training, there should be some experience gained, what worked well for you as an agent and what did not work so well. So then, after this training phase, you already have the experience. Let's try to apply this. And this is done with the secondary phase. And then you have your already trained agents who have gained this experience, and then they should make some sort of smart decision. And now we're going to look if that produces some sort of smart result, which is now similar, hopefully, to this. And the answer was yes. Also here we found some cluster, or he found, it's not me unfortunately, but starting from random positioning again, it was found that here this typical Schelling clustering happens again because these agents learned by experience how they want to relocate themselves. But a very important difference from the traditional approach to Schelling is that for the traditional, it went perfectly. So there were no unhappy agents anymore. But here, for this trained network, there were some agents who were not 100% happy because experience may not be the key to knowing it perfectly. So there is also a component which is a little bit more how the actual real world might deal with some sort of utility optimization for yourself. Okay, so now we come to the end of this talk. Just a little side note on how to work with ABMs. Of course, there's some sort of validation testing you have to do. What I didn't explain before is that for many of these models, a lot of data is used. This is another ABM that was done here for Salzburg. So you can see the geographical map of Salzburg. And what here has been done, they put in a lot of survey data on commuting behavior of people, and they tried if they can remodel the traffic in Salzburg, and it went pretty well. But how to start with a model from scratch is, of course, you have first of all a face validation. You just saw in these examples with NetLogo, you have to look if it's working right, just from this graphical information. And then you go into certain techniques about timeline tracing and some validation about stochastics, and of course a sensitivity analysis. So the model has to be robust to parameter changes, otherwise it will not be very reasonable. The last things that can be done, of course, is calibration, and then you do some sort of ensemble simulation and some statistical validation, and you end up with the results that I was showing you for these models before. However, there is some sort of limitations to the usefulness of ABMs. So what I explained to you were now agents that were not just homogeneous like particles. Particles, they're all the same. Maybe here other approaches are much more feasible, because here for the agents, they need to have some sort of different intention for their own sake, so to speak. That would be, I think, make a fine model. And also some sort of randomness is needed, otherwise it is not enough systemic behavior you find for your models. And also there are limitations due to computational power. So agent-based models go up from 10 agents up to maybe 1 million, but this depends, of course, on what you and your equipment can do. All right, so I hope I was in time. Thank you very much for your attention, and I hope this walk gave you a little insight into the landscape of agent-based modeling.